Greetings, everyone. I'm your speaker for today. I was a professor here for a while. Before that, I was a student, and before that, I got born in 1962. So here I am, still kicking. So we're going to look at timescales for Prandtl slope flow. My co-author on this is Matt Ammon. So slope flows are ubiquitous in hilly terrain or mountainous terrain. You get what are known as slope flows, thermally induced flows when the skies are clear, and typically you under dry conditions, under high pressure, and you get these throughout the world. These are quite common. Slope flows transport the heat and momentum. You have turbulent mixing, and they diffuse the heat and momentum. The knowledge of the flow structures for these slope flows could potentially guide turbulence parameterizations in complex terrain. Numerical models, including the climate models, usually treat the Earth's surface as flat. So there's no information about the underlying complexity of the terrain, even though 50% of the Earth's land surface is considered to be complex terrain. The anabatic flow is generally the upslope type of slope flow. You'll have that during the daytime when the land is heating up. And the katabatic flow, sort of the reverse of that at night, you get cold flow, and flow moves down the slopes. So one of the pioneering model that describes the slope flows is this Prandtl analytical slope flow model, dating back to 1942. It's notable for its simplicity, its physical simplicity. It's really stripped down, and its qualitative reproduction of real slope flows. And there are a number of studies that have used the Prandtl model to apply to real data cases, and at least the authors have been happy with the results of the comparisons. These are kind of qualitative comparisons, though. There's a lot of disagreements, even with the Prandtl model and real flows. But there are some similarities. Like, you do get flows of the right sense, and you get kind of a jet-like structure to it. The Prandtl model is also noteworthy in that it actually is an exact solution of the Navier-Stokes equations and the thermal energy equation, and the two-way coupling between the two is preserved. So that's partially why this is a milestone in mountain meteorology, geophysical fluid dynamics. But as I mentioned, it really is a stripped-down version of reality, and there are a number of important model restrictions that we need to keep in mind. It applies to the steady state. Okay, so we're not looking at transient effects. The slope goes on forever. There are no lateral boundaries, but the slope does go on forever. Constant slope buoyancy. The Prandtl solid frequency, or your buoyancy frequency, is set to be a constant. And we have constant eddy viscosity and eddy diffusivity. Interestingly, Prandtl actually considered the flow to be laminar, but we're going to be treating the nu and the kappa to be eddy viscosity and diffusivity, and not the molecular values. Okay, the Buzanevsky approximation is considered to be valid. Flow is unidirectional, and no ambient or background wind. Okay, so before we look at the solution for that, let's qualitatively look and see how buoyancy can drive a slope flow. Okay, so first, what is the definition of buoyancy? So we have it up here. Basically, the buoyancy is proportional to the potential temperature minus the potential temperature at the same elevation of that point that we're interested in. And then you hit it with some constants, gravity, and this reference potential temperature. So to make this a little bit more intuitive, let's take a look at the case of a heated slope. So here we've got a heated slope. Alpha is your slope angle. And we need to think about the environmental stratification. Well, the environments are typically stably stratified. Okay, so your theta is going to increase as you move up. So here's our grad theta pointing up. So now we heat up the ground, like during the daytime, we heat up the ground. It gets warm. The momentum is going to be influenced by the buoyancy in that case. The buoyancy in this case is going to be positive, and we reasoned through that, considering an air parcel here at this location. It has the value of theta 2. At the same elevation, the environment has a value of theta 1. Theta 1 is less than theta 2 because it's stably stratified. that means that your difference between theta and the environmental theta is positive. So you have positive buoyancy. The buoyancy appears in the vertical equation of motion, and it's associated with the vertical force. So here's your buoyancy force. It's the buoyancy times your vertical unit vector. And it acts purely in the vertical. Positive is upward, in this case of anabatic flow. Katabatic flow would be pointing down. But in a slope following coordinate system, up is a combination of upslope and slope normal. So a purely up buoyancy force does give you a force component along the slope, and that's going to drive an upslope flow. So that physically, that's why you get an upslope flow when you have positive buoyancy, and that this is the distribution of buoyancy you get with surface heating. But keeping in mind that this underlying potential temperature pattern here, which is largely the environmental, you can see that any upslope flow in this scenario would be bringing up smaller values of theta. So you actually have negative temperature advection, or environmental potential temperature advection would be contributing to cool the flow. So you have a negative feedback. The buoyancy is trying to accelerate the flow up the slope, but it's dragging along your environmental potential temperature, and that's going to be providing cooling, which is going to counter the buoyancy. And conceivably, if you get a balance between those two, you get a steady state. Okay, and that's kind of the essence of what the Prandtl model is about. Okay, so the Prandtl model equations, we can write them here as the x components of the equation of motion. And then we have a thermal energy equation. And both of these are expressed in terms of this coordinate system, slope following coordinate system. Big X here is the downslope coordinate, and big Z is your slope normal coordinate. And keep in mind that big Z is not the same thing as the true vertical coordinate, which is Z star. Okay. So for upslope flow, and in the diagram here, I've drawn in a sketch of the U for an upslope flow. You can see it's moving upslope. You do want to keep in mind, for future reference, and we actually look at some results, that U being negative is what you get for an upslope flow, because that flow component is directed opposite the X direction. Okay, so upslope flow, U will be negative. Okay, so here's your equation of motion. This is the buoyancy force component in the X direction. Okay, that's what sine alpha is doing. So the sine alpha in general is going to be pretty small. So it's going to knock down the value of your buoyancy force because we're looking at a force component in the X direction. Then you've got your diffusion term over here. Thermal energy equation, this UN squared sine alpha term looks a little bit weird. That's your vertical advection of your potential temperature. It's actually vertical advection of the environmental potential temperature. You don't see W in there, and that's because in the slope following coordinate system, capital U sine alpha is the amount of the wind in the W in the Z direction, Z hat direction. Okay, so it's W times n squared, and n squared is proportional to d theta dz. So this is your vertical advection of potential temperature term. And then you have diffusion of buoyancy. And I'm going to write out the incompressibility condition here. It's satisfied identically. All the terms in it are zero, which is fine. So the unidirectional flow, U is the only wind component, and U is independent of X because the slope buoyancy is constant. Okay, so we're not going to look at del dot U equals 0 anymore. It's automatically satisfied. We can forget about it. Okay, and the boundary conditions are simple. No slip at the surface. We're going to specify a constant buoyancy at the slope. And then far enough above the slope, we want the velocity and the buoyancy to go to 0. Okay, so there's no ambient flow. And this is the Prandtl solution. So we've got a solution for U and a solution for B. And you can see where the slope normal coordinate comes in, and it's divided by delta, which is defined over here. Okay, so appearing in the solution, you'll see a Prandtl number, PR, in the solution for U. Okay, and Prandtl number is defined to be the ratio of your viscosity to diffusivity. U over kappa is your Prandtl number. The delta you can interpret from inspection of what it really means. So here you've got an exponential, but with a minus in front. Okay, so it's a dying exponential. And usually when you're looking at exponentials and you want to quantify how quickly the drop-off is, you say, all right, well, at what height or time, if you're looking at a time-dependent problem, in this case it's height, at what height does your exponential drop off to roughly a third, 1 over e? Well, that happens when your exponent is -1, and that happens when v is delta. And that gives you your interpretation of delta. Delta is the height you go to for your disturbance to drop off to about a third of what you had at the surface. So buoyancy is specified at the surface. You go up to height delta, you've dropped off to about 1/3, basically. Okay. And it's a similar interpretation for u, whether you have the exponential here or here, it really doesn't matter. So the delta is basically giving you a crude estimate of boundary layer height. Okay, now you can look at that boundary layer height estimate, the delta, and you'll notice that we're dividing through by the root of sine alpha. So for very gentle slopes, your alpha is going to 0, sine alpha is going to 0, but it's in the denominator. You're dividing by 0. So delta is blowing up on you. So you have an infinite depth to your boundary layer. Okay. The Prandtl model is sometimes criticized for that. It doesn't seem physically reasonable to have an infinitely deep boundary layer. Okay, well, we're gonna say more about that because that's actually an important part of this presentation. Okay, anyway, from equation 4, from the analytical solution, you can differentiate your u with respect to z and find out where u is a maximum, and so you do that and you get your equation for the height of the wind maximum, as well as an equation for what the wind maximum actually is. And a few things to note about that. First, the height of your wind maximum is proportional to the boundary layer depth. Okay, well, that's not surprising. The height of the wind maximum doesn't care about the surface forcing. Well, that's kind of interesting. But as we've mentioned, that height continues to grow as your slope angle gets weaker and weaker. Shallower and shallower, your boundary layer gets higher and higher. The peak wind speed has a Prandtl number dependence to it. Okay, so your peak wind goes up as your Prandtl number goes down. And that kind of makes sense because Prandtl number is nu over kappa. If the nu gets small, so your Prandtl number is getting small, your Umax goes up. And you can think of that crudely or qualitatively. If your nu is getting small, it means that you've got less drag. And if there's less drag, the flow will be faster. Okay, so that's the way that I interpret that. And here's an example of what that Prandtl solution looks like. So I've chosen some values that are qualitatively what you might expect for an anabatic flow case. And in this case, the slope angle is about 5.73 degrees. Here's your surface buoyancy, B naught, typical value of your Brett solid frequency, and then 5 meters squared per second for both nu and kappa. Now, if you recall the analytical solution for u and b, they're in the form of exponentials times sines or cosines. So the way I like to think of it is this thing, you go up, it's wiggling and dies and wiggles and we see that here in the plot. The wiggling is actually damped pretty heavily. So here you've got a peak for u. Here's another peak over here, a minimum, and there's another peak probably a little bit off the scale here. Same thing for b. Both of them are oscillating as they go to infinity. Of course, the oscillation is pretty minor at that point, but it wiggles and it dies. Okay, so the question that we can ask is, how long does it take a slope flow to adjust to a sudden change in the slope buoyancy? Prandtl model doesn't tell you that because it's a steady state model. But in real life, you get changes of buoyancy. You can think of the diurnal cycle. It's warm during the day, it gets cold at night, and it goes back and forth like that. You get a diurnal cycle of anabatic and katabatic flow. But what's the adjustment time for that? So this was actually the subject of some studies from the early 1950s and 1940s in the Soviet literature. So I dug up a few of these papers, and Evgeny helped me take a look at this Gutman one. So Gutman derived an adjustment time scale of 2 pi over n sine alpha. Now that's for the case of the parameters 1. So what we're going to do in this study, I want to clarify and refine that estimate. That's basically what this study is about. But there are a number of quotes that I think are relevant and actually help motivate the study. So Gutman and Koratova state that if the inclination of the Earth's surface is quite small, the motion will be essentially non-stationary. So notice that Gutman doesn't say that the boundary layer becomes infinitely deep. He says that the flow will become essentially non-stationary. And that's an alternative way to thinking about the Prandtl solution. Okay, if it's non-stationary, it means that you're not going to get to the point where the boundary layer is infinitely deep. Something's going to happen before that would occur. And so for steep slopes, Gutman says, yeah, you can consider a stationary problem for the steep slopes. But then he cites this study by Kurgian from the late 1940s. In that study, Kurgian notes that a mountain wind is generated almost simultaneously at all heights. And I thought that was interesting because that suggests that you should be thinking about the different response times at different heights, because maybe they would be different at different heights. Although according to this study being cited, they're actually simultaneous. So, which is it simultaneous, or does it take a while for the information to move upward? Okay, so some other quotes will also be relevant for that. Slope flows react instantly to insolation. Upslope breezes start a few minutes after sunrise. Conversely, even a brisk upslope wind stops suddenly when a cloud locally obscures the sun. Okay, so that argues that it's in pretty close, pretty quick, pretty instant. And then Schumann says it will take a very long time before UBL, as an upslope boundary layer, reaches steady state at small angles because of its great thickness. So these two quotes are basically diametrically opposed to each other. And so what is going on? Is there a height dependence to the response time or not? And what is the response time? Okay, so that's what we're looking at in this study. We're going to use an unsteady version of the Prandtl flow model to quantify how long it takes the wind and buoyancy to attain their steady state after an abrupt onset or change in slope buoyancy. So you could think of it as, maybe you've got a katabatic flow at night, and then the sun pops up, and it switches to anabatic. What's the time frame for that changeover? Or you can have something going on like in this picture that I have here. It kind of looks kind of like a motivational poster, kind of had that corporate vibe. Sorry about that. But anyway, it shows the sun disappearing behind the cloud deck. Okay, so that's going to cut off your insulation to the surface. Surface buoyancy will change and you should get a response. So we could be looking at times related to sunset and sunrise, or just the cloud deck coming in for a few hours. In all those cases, there'll be a response time associated with how quickly the flow responds to the changed surface forcing. Okay, well, as you probably imagine, the talk is going to be on the theoretical side, but before we wallow into that kind of stuff, I wanted to show at least one real data case. So we'll look at some real data here. So this is an example of the katabatic and anabatic winds at a biological field station in Costa Rica in a cloud forest. So on the top, we have the wind and the gusts for a 24-hour period. So the dark curve is 5-minute wind, and the lighter curves up here are your gusts. And the yellow circles are your wind direction, and direction is indicated over here. Don't worry about what the actual wind direction is. The thing to notice is this abrupt reversal of the wind direction around 8:30 in the morning. Okay, and it changes by about 180 degrees. So at night we have a katabatic flow. So you'll have to trust me on this, that this wind direction is down the valley, or down, and it's a sloping valley. Okay, so it's not just a slope, it's actually in a valley, but it's a pretty strong slope to the valley. So you have katabatic flow at night, and the sun peeks out over the ridge, and you get an anabatic flow. So the thing reverses. The temperature change down here, and pink is your temperature, TD is your dew point. Okay, so you actually get a bit of warming between 6 and 7 in the morning. I think dawn is around 6, but the sun is hiding behind a mountain ridge. So it doesn't really jump out over the valley until like after 7. And then the temperature just takes off. It rises by about 20 degrees in under an hour. And then it levels off abruptly. Okay, so here we can see a pretty nice transition between a katabatic flow condition and anabatic flow condition. Okay, so we're going to apply an unsteady Prandtl model to kind of tease out information about the response time. And I understand these are very simple ways of representing what's really going on out there. Constant eddy viscosity and diffusivity is a very restrictive assumption. But we can at least get something with that. Okay, so these are basically the same Prandtl model equations that we looked at before, but now we have unsteady terms. You have a local change of u and a local change of v. And we're going to solve these two using the same boundary conditions that we considered for the Prandtl model. But in the present case, because it's an unsteady problem, we also have to worry about initial conditions. Okay. Well, it turns out you can use the same solution framework to two different types of initial conditions. Okay. All you have to do is like change your perception of the meaning of some of the terms. That same framework applies to both of these boundary conditions. The first one, IC1, is a thermally unperturbed atmosphere is at rest, so nothing's going on. And then at t equals 0, you turn on your forcing. So you abruptly turn on a slope buoyancy, and then you leave it on at the value B naught. Okay, so that's your surface buoyancy, it's not changing with time. Okay, and then you look and see how quickly the flow responds to that imposed slope forcing. Initial condition 2, in this case, you already have a well-developed thermally induced flow. You already have a Prandtl-like flow going on, whether it's katabatic or anabatic. And we assume that that's in a steady state. Then all of a sudden, that slope buoyancy changes. Maybe the sun disappears behind a cloud deck, something like that. Okay. In that case, we're going to let B naught represent the change in the slope buoyancy. It's not the slope buoyancy, it's the change in the slope buoyancy. So again, slight difference in the meaning of the interpretation of the B naught, but we're going to be able to work with both initial conditions under the same umbrella of the analysis framework by considering that revised meaning for B naught. In addition, though, you also have to interpret U and V not as wind and buoyancy, but as the deviations of the wind and buoyancy from what they were at t equals 0. So you have an upslope flow, for example, steady state, then it changes. The U represents the change in the U in that case. Okay, so we're going to non-dimensionalize the problem. And equation 8 here gives us the scales that are typically used to non-dimensionalize Prandtl flows, at least the spatial part. And then here we've got a time scale which has been introduced over the years in some of the studies that have looked at unsteady slope flows. You might ask, where do these scales come from? How do we know this is appropriate? So there are lots of ways to non-dimensionalize your problem. And there actually is no one right way. There are lots of right ways. In fact, there are no wrong ways. Unless you make a math error and actually put in something that dimensionally doesn't work, everything is fine. It really depends upon what you want to do with it later on. Like if you want to neglect a term based on scale analysis, then you've got to be really careful about how you choose your scales. But if you're not interested in that, do it however you want. So in the present case, you'll notice that we've got sine alpha downstairs here and also downstairs over here. And you might wonder, well, how do you know it's downstairs? Maybe you could put it upstairs. And yes, you can if you want. If you don't want sine alpha downstairs, put it up here. The reason is sine alpha has no units. The n has units, inverse time. So if you put sine alpha upstairs, you still get a perfectly legitimate time scale. The problem with that is that your non-dimensional problem will actually be more complicated if you do it that way. The sine alpha is where it is here and here, because that gives you your simplest non-dimensional problem. Okay. So you non-dimensionalize your variables using scales, and then in terms of the non-dimensional variables, ND meaning non-dimensional, this is what the Prandtl, the unsteady Prandtl setting looks like. So you've got your two governing equations here that we've seen before, but now they're non-dimensional, and then your boundary conditions are here. And what you'll notice about the non-dimensional problem is that alpha, your slope angle, does not appear anywhere in it. Alpha has been removed from the non-dimensional problem, and that's because of where we put the sine alpha. If you put the sine alpha upstairs, you get equations looking like that, but then sine alpha would show up somewhere in there. So the only parameter that's showing up in the non-dimensional system is the Prandtl number over here. Okay, so it's a 1 degree of freedom problem, and alpha doesn't show up. Okay, so that's nice. That gives us a very simple problem. Now we will care about the final solution in dimensional form, right? I mean, that's what we care about, is the actual dimensional wind and buoyancy. But we get it by going to the non-dimensional problem, which is fairly simple because it doesn't have alpha in it. Okay, so let's say that we've solved the non-dimensional problem for the wind and buoyancy. So we know little u and little b, the non-dimensional wind and buoyancy. Let's say we know it, and then we want to get the dimensional wind and buoyancy. So just focusing on the dimensional wind, because of the way that we non-dimensionalize that problem, we can relate the dimensional wind to the non-dimensional wind through this equation here. So it's got this factor of b naught over n. And you have little u is your non-dimensional solution, little z and little p is the non-dimensional height and time. That's where the alpha is hiding. It's hiding inside of the non-dimensional values here. So little z, you can relate to the dimensional z and the n and the nu, and here's your sine alpha. So the slope angle shows up at the very end when you make things dimensional. It's going to show up there. It shows up in the time as well. You get a little t is proportional to your sine alpha. So that's where you're going to get the actual alpha dependence. Okay, so if you were to make contour plots of your dimensional wind, u and d, and if you were to make those plots to different values of alpha, the plots would all look the same, but they would be stretched in the z direction and stretched in the time direction. So that's the meaning of having the alpha showing up in this manner. Okay. So the other part of it is that because the u and the b, little u and little b, are basically universal. You get universal curves from these. The only time scales that you have to worry about are the ones that, well, they're all proportional to the time scale t, 1 over n sine alpha. All of the time scales are. So you could think of a time scale as being a constant times 1 over n sine alpha, but you don't know what the constant is. Now in Gutmann's paper, the constant was 2 pi. That's 6, basically. So, what really should it be? Should it be 6, or should it be 6 million, or 0.0001? Because, knowing that your time scale is proportional to 1 over n sine alpha is great, because you can figure out the dependence on alpha. But what's the magnitude? That you don't know. You got to look into the equations, and that'll tell you then what the constant is. Okay, so don't worry about the details. The solution for u, little u being the non-dimensional wind. So the non-dimensional solution, we know, is independent of the slope angle, right? Alpha does not show up anywhere in your differential equations, doesn't show up in your boundary conditions or your initial conditions. The solution is independent of alpha. Well, it turns out we have a solution for the case of a vertical wall. And this was solved by Evgeny and I back in 2004. Vertical wall problem. So you can take the solution for the vertical wall problem, and that gives you your solution for any angle you want, using the scaling that we've just looked at. Okay, so the formula for the wind in this case, it's actually composed of 3 parts. It's a series expansion in terms of a small parameter, the Prandtl number minus 1. And so this solution is constrained to be valid near Prandtl number of 1. Okay. And in fact, you get an exact solution of the Prandtl number is 1. When the Prandtl number is 1, that drops out and that drops out. And you get u is equal to u naught, which is that first term here. It turns out that's an exact solution. It's not even an approximation. This is the solution to that problem. And then when the Prandtl number is not 1, then these terms survive. And you can think of them as tacking on almost like correction to the Prandtl number of 1 solution. And yeah, they're terrible looking. But it's not hard coding these things up, and we know what they are. And the irony of this is that it's actually easier to calculate the acceleration than the wind. This is really remarkable. Let's think about the case of Prandtl number of 1. Okay, so these terms here drop out. Your u is u naught, which is this thing here. Time shows up as the upper limit of integration, and it doesn't appear anywhere else. And the mu is a dummy variable, so you don't have to worry about that. So if you take the time derivative of this, the integral goes away, and it's replaced by this stuff here, evaluated at mu equals t. So you get a nice simple equation for your acceleration. much nicer than the wind itself. So the acceleration for this problem, it turns out, is much simpler than the wind. Okay. The same thing is actually true of U1 as well. So if you differentiate U1 with respect to time, you also get a reasonably nice expression because the integral goes away. Not true for U2, and you're going to get a mess. And well, actually, sorry, I take that back. The integral still goes away, but you're going to get a mess because of these other terms. Anyway, we're not going to worry about that. Okay, and then similarly, you get a solution for B that's even worse looking than the solution for U. Again, the thing to note is that it's an approximate solution valid for Prandtl number near 1, and it becomes exact right at Prandtl number of 1. Okay, so when we were looking at this question about the adjustment time scales, say the sun peeks out from behind a cloud deck, we want to see how the time scale for the adjustment is changing as a function of Prandtl number. That's one thing to look at, as well as a function of height and any of the other quantities, especially the slope angle too. So from the analytical expression, you actually get a nice result for the sensitivity of the wind and buoyancy to the Prandtl number. Okay, so we have the formula for for buoyancy like this, and similar one for the U. The Prandtl number is only here and here. It's Prandtl number -1, Prandtl -1 squared. The B0, B1, and B2 are not functions of Prandtl number. There's no Prandtl number there. So finding the sensitivity of the wind and buoyancy is easy. You take your, say for the U component, if you want to find out how sensitive it is to the Prandtl number, you differentiate it with respect to the Prandtl number. Okay. Now that result, the UD Prandtl number is this. So it's easy differentiating that previous expression. And we'll call that our sensitivity function. In this case, sensitivity function for U. And you do the same thing for the buoyancy. You have a sensitivity function for the buoyancy. Okay, so we're going to plot this out, and we'll do this for Prandtl number of 1. You can do it for any Prandtl number you want, but we'll do this for Prandtl number of 1. So this is your sensitivity function for the buoyancy, and here for the wind. And we're plotting the contour plot. So we've got height over here, and time over here. So t equals 0 is when we're starting out, and then it proceeds like this. Okay, so the sensitivity for the buoyancy, if you're near the ground, so Z is small, the sensitivity is blue, which is negative. So the B Prandtl number is negative. So as the Prandtl number increases, the buoyancy is decreasing. So larger Prandtl numbers give you weaker buoyancy, at least according to this. Okay, larger Prandtl numbers, you're going to get a weaker anabatic flow. And you take a look at the sensitivity for the U component, and now you can see it's positive, right? So FCU is positive, and you say, hey, wait a second, does that make sense for U to be stronger? Well, it's actually not stronger, because remember, upslope flow, your wind, your U is negative for upslope flow. So the fact that your FU is positive means that this negative U, you're tacking on something positive, you're weakening it. So you get a weaker upslope flow for larger Prandtl number, and that's consistent with the sensitivity function that you get for SB. Okay, so the acceleration, one of the nice things about acceleration is where it's 0, you can say you've got a maximum or minimum of your wind. Okay, so that's interesting. What time are we going to get our maximum wind or minimum wind? Right? Well, you calculate your acceleration and set it to 0. Okay, so for the case Prandtl number of 1, the simplest case, your U component is a U0. And as I mentioned, you can differentiate it and you get a nice simple expression in that case, and here it is. So when is the acceleration 0? When do you get your peak wind? Well, when DODT is 0. And you can tell by inspection that happens when sine t is 0. Okay, so when your non-dimensional time is pi, 2 pi, etc., your acceleration goes to 0, and you get a wind maximum in time at any height, independent of height. Sine t of 0 doesn't care what height you're at. So from that result, you can pick out the dimensional time of the first wind maximum, because it is going to oscillate. But the first time you get your maximum is at pi divided by n sine alpha. Okay. So now what do the wind and buoyancy actually look like? So let's take a quick look at the these contour plots. So they're plots of the wind and buoyancy as a function of height and time. And we look at the top column for Prandtl number of 0.5, and the lower, sorry, top row is the Prandtl number of 0.5, and lower row is the Prandtl number of 1.5. And if you look at let's look at the U component, the U field for Prandtl number of 0.5, you can see, first of all, that it starts from 0, as it should. And you get an oscillation. It's a decaying oscillation. And it peaks over here. You know, you get your largest U is peaking over here at t equals pi, right? So that's good. That's consistent with what we thought. And the flow is stronger than what you get with the Prandtl number of 1.5. Okay, so that's consistent with our sensitivity analysis, the sensitivity functions. For the case of the buoyancy in non-dimensional terms is going to be 1 at the surface, so that doesn't change. But you can see the depth of the thermal boundary layer has changed. And on the whole, the boundary layer is a weaker thermal content for the larger Prandtl number. Yep. Okay, so now we're going to consider the response times for the U and the B. So we can take the analytical solution and we can just milk it for information now that we have it. And so we can calculate response times from it. So let's let PU here be the response time for U, and TB is the response time for B. And we're going to calculate them to be height dependent. You go to any height you want, and we can calculate what these response times are. And we're actually going to go from the ground up to the height of the wind maximum. We're not going to go beyond the wind maximum because mostly we're interested, where the wind is. Okay, so we're going to look at the response time. So how are you defining response time? We're going to take to be the times that it takes U and B to first reach specified percentages of their steady state values after the slope buoyancy has changed. Okay, so the slope buoyancy changes, that the t equals 0, that starts the clock, and then we want to see how long you have to wait before you get close to a steady state, and you're free to decide how close to the steady state you want to go. Do you want to go all the way to the steady state? That means you're going to 100% steady state. Or do you just want to go up to 25% of the steady state? You define what metric you want and see what you get. Okay. And I'd say here too that the time taken for U and B to first reach specified percentages, because as we've seen from the solutions for U and B, those contour plots, they oscillate. Okay, so you're going to hit the same value several times. So we choose the first time that we hit, say, 50% of the steady state or 100% or whatever you want. That first time marks the response time. Okay, so here we're going to look at the response, and I'm showing the result here for now for Prandtl number 1, and we'll look at the other Prandtl numbers. But for Prandtl number 1, your response time for buoyancy, and this is the response time for U. And so it's plotted out here. We've got height and response time. Okay, that's for both diagrams. And you'll notice that the response time for buoyancy goes from 0 to 1, and the response time for the wind goes from 0 to 2.5. The response times for buoyancy are more than twice as fast. So it's very rapid for buoyancy, not so rapid for the velocity. So that's the first thing that you can note from this. The other thing you can note, so here we're looking at different percentages of response. If you look at the lower curve, the 25%, you can say, okay, well, how long do you have to wait before your buoyancy at a certain height is 25% of the steady state value? Okay, so that's this blue curve, 25%. And you can see that to get to 25% of the steady state, you have to go higher. Wait, how do you interpret this? You go higher up to get, well, the disturbance is propagating upwards, is what this means. Okay, that's at 25%. And same thing for the wind. At 25%, to get a certain response time, you have to 25% response time. To get that response time, you have to go higher up. And when you get to 100%, that means you first hit your steady state value. It's largely independent of height. So those quotes that we looked at early on for the onset of when you get your steady state approximately, whether it's instantaneous or if it takes a while to propagate up, they're both true depending upon the metric you use. So however you define your metric will give you one thing or the other. So, but anyway, you can see that the time scale, the response time scale for the wind is more than twice back to the buoyancy. So that was one interesting part to that. And we can look at the Prandtl number dependence. So if you look at the response time for the wind, you'll see they really don't change all that much. Prandtl number of 0.5 to Prandtl number of 1.5. You know, you're 100% steady state. You get that PU of 2. Here it's 2.25. They're pretty close. Not so for the buoyancy. Okay, there's basically a factor of 2 difference between the Prandtl number of 0.5 and 1.5. The smaller Prandtl number gives you a more rapid onset, well, a more rapid response time for the buoyancy, not for the wind. Okay, what about the dimensional response times? Okay, so now we use capital P, PU, and dB are the dimensional response times. So they're the times, the dimensional wind and buoyancy to hit the 100% threshold. So we're going to say, what time do you first hit that steady state value? It's going to overshoot the value and then undershoot it, but when do you first get to that steady state? So you take the 100% plot for TU that we've seen on the previous slide, and you normalize it with inside alpha. That is your dimensional time scale, response time scale for the wind. And you get a similar one for the buoyancy. Okay. Now we've already seen from the previous diagram that these time scales should be pretty independent of height at 100%. Okay. So in that case, instead of showing a profile of these, we may as well just take one value, evaluate this at the location of the wind maximum, because that's going to be representative of what you get at any height. Okay, so we're going to take a quick look at 2 examples, an anabatic flow case, C1, and a katabatic case, C2, but we're going to vary the alpha, the slope angle. Okay, and I've put in sort of typical conditions here for B naught and the N, and I've chosen nu and kappa to give us Prandtl numbers that are roughly what you'd expect under anabatic and katabatic flow conditions. Okay, so the peak wind, so this is basically the Prandtl steady state here. The peak winds, Umax in the steady state, for the anabatic case, for the parameters that we're working with here, the anabatic flow is stronger, so you get minus 4.5 compared to nearly 3 for the katabatic. But this is an interesting curve here. That's your boundary layer depth for the wind. Well, it's the wind maximum height, plotted as a function of slope angle. And you can see that as the angle gets small, the boundary layer depth gets huge, and it's off the chart when you get really small. We put the numbers on this, so we can see that for a slope angle of 1 degree, you've got a wind maximum at 158 meters above the ground for the anabatic case, and 66 meters for the katabatic case. If you drop the slope angle to 0.1, your wind maximum now occurs at 500 meters, so it's more than doubled. And the same thing for the katabatic case. Okay, the response time for these 2 examples, what do we get? So for the response time for buoyancy, you can see there actually is a factor of 2 difference depending upon the Prandtl number. Of course, it's not just Prandtl number that's changing in this case. A lot of the parameters have changed. But you can see that we do get a pretty big sensitivity here from the anabatic to the katabatic cases, where in contrast, the wind response time really doesn't care too much about the 2 cases. It looks very similar. But you'll notice that the response time for the buoyancy is much smaller than the response time for the wind. So again, more rapid adjustment for the buoyancy than for the winds. And we can see a curve fits quite nicely to the C1 and C2 cases. Your response time, pretty good, 2.1 over n sine alpha. So your constant C, C over n sine alpha for your response time, it's 2.1. And that's about a factor of 3 smaller than Gutmann's estimate of 2 pi over n sine alpha. So we've managed to refine the estimate, as well as show that your response time is going to blow up on you at very small slope angles. Okay, so for that 1 degree slope angle, it takes about 3.3 hours for the wind to attain a steady state, or to first hit the steady state at the level of the wind maximum. For a much smaller angle of 0.1, you get 33.4 hours. There's no way you're going to be able to fit that into a diurnal cycle if it's 33.4 hours. If you have a diurnal cycle, you want your TU to be within, say, 6 hours, even less would be good. So the criticism of the Prandtl model that it breaks down at alpha going to 0, you got to be careful with that. You wouldn't want to apply the steady state Prandtl model in this example. The Dupin was right. It's fundamentally unsteady. Okay. So you could not get a very shallow slope angle solution in the steady state. It does not make sense. Okay, so that's all I have. I'm going to briefly acknowledge some help that we've had in this. Amanda Schilling, our NWC librarian, and Nina Bumgarner from Penn State helped track down some of the literature. Bruce Hoagland and Chris Meadle helped get the, they got the Costa Rican data and plotted it up. And then lastly, I've got these guys here that made no contributions to the study at all. Actually, they did make contributions. They were negative contributions. Okay, I'll take any questions. Sure, Josh.
So the reach out to dedicate you look at first how angle, like how much of the Prandtl, how much did they think you would reach kind of diurnal time scale kind of that I feel like they get out like
where are you? No, I haven't. You could infer the information off through the app from the plots that were presented. You could back out that information graphically with a pen and paper. You could just graphically do that. I didn't do it, but it could be done based on the information we have. That's a good question, especially if you want to parameterize this stuff. That's a really good point, because there's still, even if you don't get a steady state, there's still useful information you could extract about how far you can go in, say, 3 hours. That's still useful information. Yeah. You get it? And that was Schumann's point. That's exactly right. Yeah, you wouldn't want to apply this to a flat. I mean, you get nowhere applying it to a flat, because the boundary layer would continue to rise. I mean, physically, it kind of makes sense that you keep pumping in heat forever. It's just gonna keep rising.